Hi, this is my video number 31. Okay. In this video, I'll talk on the Laplace transform. Yeah, Laplace transform. From the Fourier transform, yeah, we have this definition. Gx is given by that 1 over 2 pi. There's double integration and so on. And if we we suppose gx is equal to here minus, I think in the notes some mistake typing error there, minus cx hx fx for c positive. So we have so that gx equal to 0 for x negative, then those formula becomes that. Okay, and then if you let that, and those equation becomes this. Here you have e exponent u of ux, yeah, exponent ux, again typing error. Then the Laplace transform of fx is defined as there L fx u fu, integrate from 0 to infinity, all those things, and the equation formula is given by that. Okay, so let me write down the Laplace transform. So the Laplace transform of fx, yeah, transform of fx, we denote that as L f of x u as fu, this is equal to minus 0 to infinity e minus ux fx dx for real of u is positive. Okay, so we have those things. I think this is again typing error here. Yes, and the equation of the Laplace transform, inversion of Laplace transform f inverse. That one is u. This is, we obtain fx given as this c minus I infinity c plus I infinity eu x fu du for c positive. Okay, so that's the inversion of the Laplace transform. So we have two things here. We have a Laplace transform, then the inverse of the Laplace transform. So we have the related theorem to the Laplace transform. We suppose fx is integrable over every finite interval ab. You remove that part here, okay, where a is smaller than b. Then there exists a real number c such that for arbitrary b positive, the integral b to t, capital T, exponent ct ft dt tend to finite number as t goes to infinity. And for arbitrary a positive, the integral epsilon a ft dt, absolute of ft, tend to a finite limit as epsilon goes to 0 from positive. Then the Laplace transform exists for the real of u is greater than some number c. So this theorem ensures the existence of the Laplace transform for the function f satisfies these two conditions. Okay, So here is the proof of that theorem. What we want to prove is we want to show that the existence of the Laplace transform, provided that our f satisfy these two conditions here. Okay, so for the proof, if a and are arbitrary and epsilon less than a and suppose c positive, then we have this. Okay, we consider that absolute of those, and then taking the absolute inside, we have that less than. Okay, and we know that c is always positive, and as t getting bigger, those are basically bounded. So we have this is less than integral epsilon a ft dt. And if c negative, so we have this epsilon to a e minus c, we consider it negative, so minus p. So we have all this thing, and again it's less than some integral of absolute ft dt. So thus the integral 0 to a e minus ut ft exists for arbitrary a, and note that 0 to t, you can split this thing a to b, 0 to a to b, and b to t, e those things, and letting t goes to infinity. And using the given condition, the given condition is we have each of this integration is has a finite limit, so it shows that our condition is our result is correct. Then here the basic result that are easy to establish. I think you can do this. Suppose fs is the Laplace transform of ft, then le a t ft is equal to f u t. So I think you can do that. Maybe I can so it is for this you can yeah, if you have L, we do the Laplace transform of e minus at ft. Use the definition of Laplace transform. So what we have, this is, we integrate from that, give you fu. No, sorry. So if you do the Laplace transform 0 to infinity, so we have that we consider all this as our f. So we have e minus ux. Our f is given as e minus ax fx dx. Okay, so that you have 0 to infinity e minus u plus ax fx dx, and this is just the Laplace transform for f u plus a. So that's our result. Okay, so it's easy to prove that one. And the rest, for that you just need to integrate many times. You can get those things. Use integration by parts, and as well for that. Okay, this is an example of few example. We try to find the Laplace transform of x to the mu, x to the mu. We use the definition of Laplace transform, and with those kind of substitution, you can have that, and this is just equal to, and this part here is the definition of gamma function. So you can write this as a u mu minus 1, the gamma function of mu plus 1. Okay, and then for this example here, this example, I just read here and give you some explanation how to do in certain parts. Okay, so if you consider we want to evaluate this, which means we try to find the Laplace transform of eiat dt. All right, so this is, by definition, we have this. Okay, and how, in order to solve this, so you need to expand eiat as a cos at plus I sine at. Okay, we need to use this for that. Okay, if you substitute those things with EIT with that, so what we have, 0 to infinity E minus UT EIAT dt, that give you 0 to infinity E minus UT cos at plus I sine at dt. Alright, and of course you can split those real and imaginary parts. You can have 0 to infinity E minus UT cos at dt plus integrate 0 to infinity, so I can take out I sine at E minus UT at dt. Okay, and from there, this is not difficult to do. Okay, I just leave it to you to evaluate those things. You can differentiate, integrate by parts, use integration by parts twice, then you can have those give u over u squared plus a squared, and for sine we have a over u squared plus a squared. Okay, that's the solution for that. And then if you combine this, you get what the we have I here, that. Okay, if you combine this, we got what we want from the question here, that. Okay, and then the next example, if you consider the Laplace transform of the Bessel function, the Bessel function is defined as that j naught ax 2 over pi 0 pi over 2 cos at cos theta d theta. Okay, so if you do the Laplace transform of this, all right, we have 2 over pi. This is from the Laplace Bessel function. 0 to infinity, this is the definition of Laplace transform. E minus ut, and then this is from the our function, the Bessel function. Okay, you rearrange this, and we end up with that. Okay, now from here to here, what you need to do is you differentiate, integrate respect to t, integrate respect to t twice, then you can get from there to there. So I don't want to show this because this is just a standard integration. You can do it. And from here to here, in order to evaluate this thing, so you need to do some kind of a manipulation of those. All right. So this is, I suggest you can factor out u squared. So you have look at the denominator, right? You can factor out u squared. You have this 1 over a cos theta over u squared. Why we do this transfer? We write like this because we have 1 plus 1 plus tangent squared theta. This is equal to secant squared theta. Okay, this is the identity of trigonometric identity. So if you substitute a cos theta over u with tangent, that a cos theta over u with tangent, maybe I have to use different, I can use t here because we have t, or you can use different symbol, all right, different variable. Then after having this, after doing this, you'll come up with the down there we have a secant of theta, and then we need some square root, and then we have secant, and then you just keep on doing that, and you might need this triangle as well in order to solve, yeah, because tangent t is given by this, or tangent is opposite with what we call this opposite and beside, yeah. So a cos theta over u, so you can find what hypotenuse is. Then from there you can proceed. So I just leave it to you for that. Okay, so that's the Laplace transform and some example of the Laplace transform. Now we go to the convolution of the Laplace transform. Now how to find the Laplace transform of the convolution of two functions. So if we suppose that Fs is the Laplace transform of f and Gs the Laplace transform of g, then the convolution of Fg is defined by this. Here we have I have this defined the convolution of two functions. So f and g is defined by that. In the previous example I use zeta here, but in this case I use tau. So then we have this theorem, the convolution of two functions, convolution of two functions, Laplace of convolution of two functions, we have that. Okay, just multiply those convolution of first function, Laplace transform of the first function, and with the Laplace transform of the second function, and the inverse of Gs, that will give you again the convolution of f and g. Now to prove this, the proof provided here is quite tricky, so I will try to prove in the opposite way. Okay, let's try this. Now we suppose that, or we let the Laplace transform of fx u as fu, we define this as integrate 0 to infinity. This is just the definition of Laplace transform of fx dx, and L of the second function g u, that gives us, let's say, f or g u, this is integrate from 0 to infinity e minus ux gx dx. Now remember that x is the variable of integration, or we call it also dummy variable. So I can change x with other variable, let's say t or whatever, s. Yeah, so it doesn't change the meaning of this. So if we consider the multiplication of two Laplace transform f and g, so f of u multiplied by g of u, yeah, so that will give us integrate 0 to infinity, integrate 0 to infinity. So we have e minus u x plus t fx gt dx dt. Okay, here in this case I change x, variable x to t. So we have this thing, and this will have you can rearrange this 0 to infinity. So integrate 0 to infinity. So we have e minus ux plus t fx dx gt dt. Okay, and then we change the variable. Let's say mu is equal to x plus t. That gives us x is equal to mu minus t. So what happened, we have substitute into that, we have this is integrate from 0 to infinity, and we need to change the limit as well. So the limit becomes t to infinity. This is obvious because when x equal to 0, our mu equal to t. When x infinity, so mu is infinity. So we have e minus u mu f mu minus t d nu gt dt. Okay, and then you can just rearrange this thing. That will give you integrate 0 to infinity, integrate t to that. Yeah, you just combine those. We have e minus u mu f mu minus t d mu. We have f and gt. So we have gt d mu dt. Okay, and then we reverse the order of integration by reversing the order of integration. So we have those from 0 to infinity, and then here instead of t, we inverse those. So we have 0 to mu, as mu goes to infinity, so we got goes to infinity. So you can have those things. So e minus u mu f mu minus t gt dt d mu. Okay, so that will give us integrate 0 to infinity. So we have e minus u mu. Inside there we have integrate 0 to mu f mu minus t gt dt. dv. So this is the definition of the convolution of f and g. All right, so therefore this is just equal to, this is the definition of convolution, and whole thing is the convolution of Laplace transform. So basically this gives you L f g of x, right, u. Of course, there are example for this, for the convolution. I think I'll give the example in the next video. So basically, in this video, what I've done is that I give a definition of what is the Laplace transform and the inverse of Laplace transform, and we give the quite important theorem about the existence of the Laplace transform of a function where the function need to satisfy certain condition, and also as a couple of very basic result or properties involve the Laplace transform, and as well as the convolution of the Laplace transform of the convolution of two functions. All right, so I stop here for this video. Thank you.